Okay, so we're going to pick up where we left off, and we're going to continue with our geoprocessing and spatial analysis lectures. And so this week we're going to talk a lot about spatial joins. So we've talked about attribute joins before, where we take an attribute table that has data but no spatial information, and we join that with spatial data, which has spatial data but no attribute information. So we have the population of Georgia, or we have some sort of population metric by state or by county, but and then we have our spatial data. We have our counties, our states, and we join those together based on our FIPS code or some sort of common ID. And so that's an attribute join. Well, this week we're going to talk about spatial joins, where we have two spatial data sets, and we want to join their attributes based on their spatial locations. And so in ArcMap, let's add some data and get started. So we'll add our congressional districts to start, and then our schools. So public health is interesting because, regardless of whether we can zoom into Georgia here. So regardless of whether you're working at a local health department, a state health department, CDC, WHO, right? You always report to a board or some sort. So, if it's a local health department, you've got your local health board or your health commissioner who has oversight, right? So at the CDC, when I was there, obviously there was congressional oversight. And so sometimes you get requests from lawmakers, you get requests from administrators for information. And so not all work, right, that you do in public health is done, right, to essentially better the public's health. It's simply done sometimes to fulfill the request of government, or it's done to fulfill the request of politicians, or it's done to basically, as a data request from somebody higher above you. So that's kind of the scenario that we're working with here. We've got these congressional districts, so let's turn off our schools layer. And we've got our congressional districts in Georgia, and these are old, I think, but you still get the idea. And these are not your typical congressional district, or not your typical boundaries, so congressional districts don't line up easily with counties or tracts, so we can't really join data that way. We can't have a lookup table, that says, tract A is part of congressional district 1, right? Because let's add our Georgia SVI. And so we add that, and we'll change our congressional districts to a hollow fill and add our outline width. And we zoom in, we can see, we toggle them on and off, see how some of these tracts, right, basically split or are split by congressional districts. So if we're working with tract level data, we can't really have a lookup table of sorts, or we can't really do any sort of attribute join to join congressional districts to SVI, or really congressional districts to any sort of population information. So that's where our spatial join comes together, because we basically need to take the location of something, in this case congressional districts, and join it to the location of something else. And so that's what we're going to do in this lab. We're going to work with, first joining congressional districts to schools, and basically so we can answer the question, what schools, so we've got our schools layer here, what schools are each of these congressional districts in? So we could easily say, okay, I click on my I click on my identify tool and I see, okay, this is Karen Handel. It's the, here's the district ID. Here's all my relevant information. I click on my school. Okay, this elementary school is here. Well, that's very tedious. So what we want to do, though, we want to join that information. And so there's a couple different ways we can do it. So the first and easiest way to do it is simply by right-clicking on the layer, going to join and relates, just like we would an attribute join, and selecting join. And now, remember in our attribute join, we have join attributes from a table. We can specify the table, specify our fields. Well, up here, we can say join data from another layer based on spatial location. And right away, it says congressional districts, or we could choose SCI if we wanted, but we'll stick with congressional districts. And then, so basically, we're joining polygons to points. So basically, if we, are joining points to polygons, it gives us different options. So this, because we're joining polygons to points, this is actually very similar to the intersect. So for this methodology, we could actually use an intersect of the two, of the schools and their congressional districts, but for this application, I wanted to show you the spatial join. So basically, each point will be given the attributes of the polygon that it falls inside, which is exactly what we want. We want each school to have the congressional district attribute. And then we have an output, and we can specify that output. So we'll click Save, and then that's it. So we click OK, and then it'll run that spatial join, and then it gives us a new output feature class, right? A new school feature class that if we click on the school point, now not only do we have the school information, right, but we also have the congressional district information. So if we wanted, we could come in and we could symbolize that data based on the congressional district name, right? So, that is a very, very, very simple example of a spatial join. We're taking attributes from one layer, the congressional districts, and joining them to another layer, the schools, based on their spatial location. So let's take a look at something a little bit more complicated, and that's joining polygons to polygons. So let's turn these off here, and let's turn on our SVI. So this gets into, that was a great example because it just shows you the basics of spatial joins, right? It's not a hard concept, and so that's kind of what I wanted to illustrate. This next example really kind of gets more into the public health aspect of, we have a health-related data set, and that's our Georgia SVI. And the SVI, again, if you remember, is something that the CDC has put together that helps identify social vulnerability in communities, right? So there's physical vulnerability, right? So there's, is your community physically vulnerable to disaster? Does it have levees that can break? Does it have lots of buildings that aren't structurally sound to survive earthquakes? Does it have those sorts of physical vulnerabilities? The social vulnerability aspect is more related to the makeup of the community and how resilient the community is to natural disasters and how well and how quickly they can recover from those disasters. So it's certainly feasible that Congress members would want to know the social vulnerability of their congressional districts and their constituents in their congressional districts. So, what we're going to try and do is we're going to try and show, the average, or, basically the social vulnerability of each congressional district, right? And so we've got our social vulnerability here, right? And if you remember, we've got all of these dozens of attributes, right? We have all the attributes that, the actual estimates, which are these numbers, the E, the margins of error for those estimates. We have the percentages, the percent margins of error. We have the rankings for each one of those. We have the themes, and then we have the final actual ranking. We have these flags. So we have just a ton of data for this information, for this SVI. So, if we zoom in here, we turn this on. Let's take a look at what happens. So say we were to right click on this and go join like we did before, right? Join not schools, but Georgia SVI, right? So now we have different options, right? Each polygon, because we're joining polygons to polygons, each polygon be given a summary of the numeric attributes of the polygon in the layer being joined that intersect it, right? And a count field showing how many polygons intersect it. Okay, that's great, but there could be a couple issues here. First off is, let's take a look at what happens when we just highlight one of these. So let's highlight you. Actually, you. Hold on a second. Let's make you. Let's highlight you. Okay. And then let's make you selectable again. And so now I just want to do a select by location. So this will give you an idea of if we do that join, what some of the census tracts are, the SVI tracts that will intersect this location, right? So because see how we have these inconsistencies in this boundary? So that means because this boundary goes over here, let's do this. Let's actually select by location, select features from SVI that intersect congressional districts, use my selected features, click OK. And so notice now we've got, and we'll turn off this one. We've got all of these other features selected, more than ones that were just in. Let's turn this one off. More than we're just inside this boundary, right? Because we have this boundary that crosses over, that splits these districts, right? Or that splits these SVI tracks, right? So it goes right down the middle. So if we were just to run this, this join, right? Join spatial attributes, join, using this option, this congressional district here would get the attributes from this tract, and then this congressional district would also get the attributes from this tract because they both intersect this tract. Which now, for this tract, maybe that's not bad because we're splitting the difference, and so maybe, the averages should count towards both. But when you run into issues like this, right, clearly this is just data inconsistencies with the way the boundaries are drawn. This should, these should line up, and maybe it's because we're using different resolutions of data. But we'd essentially get these slivers that are going to throw off our averages and throw off our data counts, which we don't want. That's going to cause a problem. So that is, that's one of the issues when you're joining polygons to polygons. The other is, if we remember looking at our attribute table, how many numeric fields we had. We had dozens and dozens, and we probably have 60 or 70 of these fields, right? There's so many fields. There's a ton. So also, one thing we want to do is we actually need to get rid of these two. We need to filter those out because we don't want those affecting our averages, but we can do that later. So, maybe we don't want to calculate the averages and the sums for all of those. Maybe we just want to pick and choose and be more specific. We can't do that with this tool, right? When we do that with this tool, we have to just do average or sum for all of the numeric values. We don't get a choice on what we get to do. So we'll go through both ways, and I'll show you each one first. But first, let's remove those negative 999 values. So we'll just query those out, and we'll say, where my final theme is not equal negative 999, because I know that negative 999 means there's no data for that record. And so you can see some of these mainly because they're tracks without any population. So we don't want those counting towards our average. And so just to kind of wrap up the thought based on these intersecting points, that's primarily the reason we can't do any intersects either, because if we do that, then this tract, which one does it, which congressional district does it get? Does it get assigned to this congressional district or this congressional district? So the easy way to reconcile this is to convert our census tracts, or to convert our SVI tracts to points, right? So to create a centroid at each one of these census tract points, so there's no ambiguity as to which congressional district they fall in. So we can do that in our toolbox, right? We can come to our data management tools, features, and then feature to point. So again, data management toolbox, feature toolset, feature to point. So basically, it's a pretty simple tool. We just have our input feature of our SVI, and we select where we want to save it. In this case, I'll call it GA SVI point. And then this basically says, do you want that centroid to be inside of your original polygon? Because if we have an oddly shaped polygon like this polygon here, right? So it goes over here, up here, down here, over here. The centroid might actually be right here, and that's outside of the polygon. So this basically forces, by checking this, it forces the centroid to be contained within this original polygon. So we want to keep that checked. So we'll click OK, and when we do this, it maintains all of the attributes. So we'll click close and see now we've got all of our attributes, all of our points for all of our census tracts. And if we open this up, we have all of our attributes, right? So now that eliminates any ambiguity. So here, right, this census tract, it was split by this congressional district. Now, right, this centroid basically is going to be assigned to this congressional district and only this congressional district. So that helps us solve that problem. So now we can go about joining our points to our polygons. And there's, so we could use this method. We could go join spatial, join database from a spatial location, and we could sum all these. We could do a sum, an average, but we don't have any really fine-grained control over the attributes. So I don't want to do that, right? I want to use the tool in the toolbox. I want to use the spatial join tool. And that's located back up in the analysis tools. So we've got analysis tools, overlay toolset, spatial join tool. If I open that up, this is my spatial join tool, which gives me a lot more control over what I'm doing as far as the spatial join. And so we've got all our different inputs for the tool. And the first one here is our target features. And so your target feature is what the data is being joined to. So think about this as this is the output shape that you want to keep. So in our case, it's congressional district. So we want to join our SVI to our congressional districts. So the target feature is always the last part of that statement. So when we did the first example of the schools in the congressional districts, we joined the congressional districts to the schools, right? So the target feature was the schools, and the join feature was the congressional districts. Well, in this case, it's reversed. So we're joining our SVI points to our congressional districts. So if you think about it like that, what are you joining to? That's the target feature. Your target feature starts with a T. What you're joining to, the 2 starts with a T, that's always your target feature. So that's our congressional district and our join features. So this is basically, the first part of that statement. So we are joining blank. We're joining our Georgia SVI points to the congressional districts. And we can select that. So what's this little warning say? So there's a data conflict. That's okay. We're running 2 different datums. No big deal. So we'll do this. GA, SVI, Congress, SP join. And so now there are 2 different join operations here. And you will most primarily always want to stick with join 1-to-1, and I'll kind of do a little graphic here to explain the difference. So say we have our rectangle. That's a weird color. Let's change that color. Let's just make it black so you can see it. So pretend this is our congressional district, right? And we'll make some different points here, right? Let's make those a different color, right? So let's copy some of these. 3, 5, right? So say we're joining our points, right? So these are our Georgia SVI points right here, and we're let's do a little fancy arrow here. We're joining those. Oh, that's weird. We're joining those to our congressional districts, which is great. So in the join 1-to-1 operation, what happens is when we do that join, we get our output, which is the same spatial type as the target feature. And that's always the case. So because our target feature is a polygon, our output is going to be the same as our target feature as far as shape and type. Right? If our target feature were our GA points, the output would be the GA points with the associated join feature attributes. So we have our output target feature that has all of the attributes of the GA SVI, as well as a count of 5. You know what? It's probably black. Oh, really? Come on now. As well as a count of 5. Basically saying there were 5 features that joined to this target feature, and here, is the sum or average of all of their numeric attributes. So it's giving you basically the summary of all of these attributes that join, and it tells you how many joined. If we do this, and we do, so this one is the 1-to-1. So we'll do this 1-to-1. Here, right? If we do the 1-to-many, right? So we bring it down here. So what happens is we still get the same target feature output, but we get one output for each joined feature, right? So we get 1, 2, 3, 4, 5, right? And each one of those target features has the specific attributes of a joined feature, right? So that's why it's called one-to-many. We just have one target feature, right? So this target feature right here, my congressional district, has all the same attributes, right? This is the same congressional district. It has the same congressman or congresswoman. However, this SVI point is different, and it has different SVI values because there are 5 different points. That's why it's called one-to-many. One congressional district, many SVI points. This one's called one-to-one because there's one target feature, and it gives you one join feature with the attributes that are aggregated. We will most likely always do join one-to-one. Now, we get this really cool field map. So this is what we didn't get in that other version, right? We didn't have that field map. So we couldn't specify on a field-by-field basis what we wanted to do. We just had the choice. For every field, did we want to do the average, the sum, the min, the max? And so we wanted to do all of that. We'd have 100, we'd have hundreds of fields, which would be, way too much. But this one, we can specify on a field-by-field basis what we want to do, and we can remove fields. So I can click on a field, I can click delete. I can click delete, delete, delete. So basically, I don't want all of these extra fields. I don't have to have them. I can delete all of these fields. So I only really am interested in this RPL themes field. So unfortunately, there's not a way to delete all of them at once. So I just have to go through kind of one by one. I won't delete all of them because I just want to show you. But now, in order to specify my aggregation method, I can right click and I can select merge rule. So see all of these different merge rules I have now? So in the other method, I only had min, max, mean, sum, standard deviation, and maybe one more. But now I have all of these different ones, right? So if I wanted, I could, for my RPL themes, I could do multiple, right? I could come in, you know what, let's do that. Let's just get rid of all of these. I don't need these. And this is just, this is something we can't do with that other tool, which is why I'm showing you this tool. Right? So now I've got my RPL themes, and I can actually rename this. So I can go SVI average, and I can change my merge rule to, where's my mean? There's my mean. I can add another field. I can call it SVI median. We'll keep that as the alias, and we'll make it a double. So I'm creating a new field. I can set my merge rule to median. And now notice how there's no plus symbol because there's no field associated with it. So I can right click, I can add an input field, and now I can go back and I can specify my GA SVI RPL themes, which is my final SVI field. And now I have two fields being calculated from my same SVI final theme, final ranking. I have an average and I have a median. I can't do that with that other join tool, which is why I'm showing you this spatial join tool, because it's so much more powerful. And so I can add that. Let's add one more. What do we want to do? We're double. It already will show us a count, so we already know how many records there are. You know what? That's okay. We don't need to do another one. We'll just do these two. Intersect option, basically saying if a point is in the congressional district, then it will sum up the attributes. And then that's it. So we can hit OK. So now it's going to run. And so it's running, and it ran. Great. So now notice how I have a new output feature, my GA, SVI, Congress, SP join, and it's the same shape and type as my congressional districts. But if I were to click on a point, I would see now I have an SVI average and an SVI median. So that is based on those input points from all of my SVI variable, or all of my SVI centroids in the state of Georgia. Those are the average SVI rankings. So if I wanted, I could come in and we can filter out, because we're only interested in Georgia right now, because that's only the only SVI we've downloaded. So we can do a definition query. We can say state abbreviation equals Georgia. Okay, apply. Right, and so now we just have Georgia, and now we can visualize them. We can go quantities, graduated colors, SVI average. We'll do 4. We'll just do a different color, and then there we go, right? And so now we can see on a congressional district basis, right, the average SVI ranking, right? We could also see, if we look at right, so we see this, this band across South Central Georgia that has higher SVIs, and if we were to look at the actual Georgia SVI, we would notice a similar trend, and we can do that if it ever turns on quantities, and we'll actually do this real quick just to show you RPL themes. We'll do quartile, do 4. Actually, we'll just do natural breaks. Okay. Turn that on. So, we've got similar trends overall. Not as much social vulnerability up here. So, it's interesting, but basically the point of this exercise was to show you how to aggregate spatial data, how to join spatial data based on location, and while doing that, aggregate data values as well. So the next lecture, the next video lab in the series, hopefully I'll post tomorrow night, we'll get into some, I think, really cool examples where we're essentially using the same process and the same methodology as John Snow, just with modern technology, to find answers to why hypothetical disease outbreaks might be occurring in certain locations.